Hi, in this video, we're going to take a look at principal component analysis and biplots for composition data. Okay, so composition data is data where we have proportions or percentages or parts per million going on, something where I'm not interested in the actual amount in the observation. I'm interested in the proportion relative to the other measurements. So think about the situation where we scoop up, we're doing soil samples, and some soil samples are going to be bigger, some are going to be smaller. We're not going to have 100% consistency, but what we're really interested in is proportionately how much are the different components in the soil sample. And so there we could represent everything in terms of one. So we'll rescale our observations so that the total amount is equal to one, or maybe 100 if we want percentages, or maybe 1,000,000 if we want parts per million. So there's several ways that we can go about it. And then we're going to take the focus of principal component analysis and specifically using biplots to understand more about our principal components. So what we're going to be going over is modified from geostatistics or compositional data with R, chapter 3. It's section 3.3. Here are the names of the authors. University of Central Florida students can download the textbook for free through the library. Here is the GM Geostats package CRAN page. Here is the CRAN page for compositions, and here's one of the author's professional websites. So let's get into it. All right, so principal component analysis converts our data to a different coordinate system where the new coordinate system is more tuned to what our data has. So when I take my data normally, my coordinate system is in relation to my measurements. So if we have like aluminum, silicone, and iron in our data, which we have for the examples I'll show, it's my coordinate system is in relation to how much aluminum do I have, how much silicone do I have, how much iron do I have? Well, it's going to work out that some variables are going to be correlated with each other. Some are going to not be correlated with each other, and we can actually get a coordinate system that is more tuned to the space of the dots, how the dots as a cloud in higher dimensional space are shaped. And so what we can do, we can take principal component analysis. Here, the columns of our data is orthogonal or perpendicular to each other. The distance between points in the original coordinate system is the same as the distances between the points after I set up my new coordinate system. And so this is a translation, rotation, and reflection of my data potentially. Typically, rotation is the main one. And now, if I center and scale my data before I run principal component analysis, the distances will be the same as the rescaled version, not the original data. So we have to be mindful about that. Also, the nth coordinate in the principal components, the nth component, the direction of that in higher dimensional space corresponds to the nth direction of greatest spread of our data. And so the first principal component is along the greatest spread of our data from like a Euclidean geometry point of view. All right, so let's go ahead and say that Y is our centered and scaled data. So I've subtracted the mean divided by standard deviation. And let's say that S is the matrix I get from taking Y transpose Y and multiplication divided by N. And so thus S is our covariance matrix. Well, by how we just did this, S is a symmetric square matrix, and it'll have dimensions of the number of columns for the square. And so it's a symmetric matrix, which means it's a normal matrix, which means it's unitarily diagonalizable. There's a lot of linear algebra going on in those sentences, but what this really means for us is that I can decompose any symmetric square matrix into a unitary matrix times a diagonal matrix times the unitary matrix transpose with the conjugate transpose. And so here, that diagonal matrix, since this is a symmetric matrix, this is going to have non-negative entries. All right, so what we're going to do, we're going to set up that that my largest diagonal entry is in the first diagonal position, second largest is in the second position, third largest, and so on. So that in the lower right-hand corner of the diagonal matrix, that is my lowest like eigenvalue. Oh, so the diagonal values are the eigenvalues of S, and these will correspond to our measurement of spread with our data. So lambda, capital lambda, is a diagonal non-negative square matrix with decreasing values on the diagonal. So, and Q is an orthogonal or unitary matrix. So Q times Q transpose will be the identity. All right, and so the diagonal entries of lambda are eigenvalues, and the columns of Q are orthogonal eigenvectors of norm 1, and these are the principal directions for us. Q represents a generalized rotation of the data space where the covariance matrix becomes a diagonal matrix. And the eigenvalues are the variances of our rotated data. And the scores of the rotated data can be obtained by hitting our original data matrix or rescaled data by Q on the right. All right, so we can obtain the principal component analysis from composition data, just like I can any old data, by taking Y as centered and by doing centered log ratio transform composition. Now, in my slots of principal component analysis, I have several different slots. SDEV is the standard deviation of the principal components. And this is standard deviations of the rotated data, the square roots of those eigenvalues in lambda. The loadings, this is the matrix of variable loadings. So this is the matrix columns of the eigenvectors, that's a Q. The center is the mean that was subtracted from the data set when we did our centering. Scaling is the scaling when I divide to do centered scaling. Score is the transform data, the new coordinate system, and call is just the function call to get it. All right, and so compositions has a special version of PrintCom to be able to do principal components on our composition data. And so here we're doing centered log ratio data. So I take my compositions, I do my centered log ratio to get it into a better geometric format than the original version. And now this PrintCom, this method is calling the compositions package and getting a special version for the data that we have. And you'll notice I have, the results we talked about previously. Now here we can see the output when I just print the results. And so you can see that this is the standard deviations, and you'll notice that they're going from largest to smallest all the way down to 0, which makes sense because remember with composition data that everything always adds up to 1. And so I have a low rank matrix by at least 1 every single time. And so the last eigenvalue has to be 0 every single time with composition data. Now the summary, we take our standard deviations, same values that I have up here. You'll notice that there are the standard deviations. Here I have the proportion of variance accounted for by each component. And then I have the cumulative proportion of the variances accounted for here. Now the Scree plot is a way for us to decide when I do dimension reduction, how many composition or components do I need? Can I get away with just 1, 2, 3, 4? We don't typically, when we do principal component analysis, we're doing a dimension reduction to reduce things down to a more core set and to prevent overfitting when I'm doing supervised learning. So the Scree plot is a bar diagram of the eigenvalues, and this is used usually for evaluating the variances of our principal component. And we use this a lot of times to say, hey, I only need 5 out of my 9 principal components to have, practically speaking, all the information that's in my data. All right, so here we can take a look at the proportion of variances. And you can notice that practically speaking, 5 components captures almost everything in my data. So it would not be a huge loss to just use these 5 principal components instead of the full data set. if I needed to. And so let's go ahead and take a look at that visually. Here's a Scree plot, and you can see that after 5 principal components, I've got just about everything I'm going to get in terms of the variances. The first component is the one with the most variance accounted for in the data, the longest spread, and then perpendicular to the direction of first component. Second component is the most spread direction that's perpendicular to the first. Third component is longest spread direction perpendicular to first and second, and so on. And so we can see that we capture, almost everything that's in my data from an information point of view with 5 components. I don't need the full data set. Now, the biplot is a way for us to understand our principal components. So what we're going to do is we're going to plot typically the first 2 principal components. Whichever principal components I'm interested in, I'm going to put them in the biplot. Typically, we go 1 and 2, maybe 1 and 3, 2 and 3. To try and understand things better, to understand what is going on. So the biplot is a simultaneous display of the loadings. So that's how each original variable contributes to the principal components, and the scores are the transformed version of my original data. And so this way we can see the spreads of the data and of the loadings, and the loadings are scaled by the standard deviations of the principal components. All right, and so now here I'm just putting down the data in a scatter plot. So I've taken my original data, I've transformed the coordinate system, and I just slapped it down onto the page. And so we can just see, what's the spread of our data as a cloud of dots. And we can see, up here, there's definitely a different population going on with this lithotype. We also see that we don't have very many basalt going on. Now here I can put on the loadings. All right, so how far an arrow goes to the right or left indicates how much that variable contributes to the principal component. So we can see that going far to the right is Mn, far to the left is the aluminum 2, oxygen 3, silicon, oxygen 2. And so we see that these are the main ones going out. Now, all of them are contributing a little bit, but the primary heavy hitters are these, okay? And so we would definitely be interested in those. So now, and I'm judging that by how far left and right the arrows are. Now, for the second principal component, I'm going to look at how far they go up and down. We see that Mn, Al2O3, and silicon oxygen 2 are contributing positively to the second principal component, and then we have the others over here. And so the first principal component is really picking up the difference between Mn and these two, like as a contrast. That's the primary drivers of principal component 1. Now, principal component 2 is a contrast between the primary 3 and everything else. All right. Now, also we have the fortify function that will take our data, original data, and then put on the principal components appended onto there by a column bind very nicely for us. And so here, this is from the compositions package, their version of the biplot, same information, just presented in a different way. All right, so let's look at a hard example, and let's look at using the biplot to get more information about the situation. A compositional biplot can help in elucidating the compositional dependence structure, provided that the proportion of variance explained by the first 2 components is high enough. And so what this is saying, if the proportion of variances of the first 2 is pretty big, then we can use the biplot to understand the entire data. If labels of 3 or more components fall along a line, these components form a subcomposition strongly dominated by a one-dimensional trend. All right, so let's look at that. You notice that these 2 are close, and so here, if these kind of form close to a straight line, and since it's close to a straight line, let's go ahead and plot that and see if it's dominated by a one-dimensional trend. Now, on this ternary plot that I'm about to show you and all the future ones, I centered and scaled the composition data to give a more powerful impact on what's happening. And so here you can see that I have that linear trend going on. I have Mn and then aluminum 2, oxygen 3, silicone, oxygen 2 are on the other side. And we can see that it kind of looks like a horn shape spread out. These are tighter together if I would not center and scale the data. This composition data is transformed to not have the transformation get rid of this line in the code. And we can see it again using the base, the compositions package. And you can see it tells us what the line looks like. To get that line on there, we need to have PCA equals true. Now, if the labels of two components are applied close to each other, then these components are practically proportional. And a ternary diagram with these two variables will show data falling on a line. And so we're going to look at the example here and look at how tight these are on a line. Isn't that, I mean, that is shocking to me. So let's take a look at this again. So we have PFE and go up here. Yeah, so you know, composition residuals and FE is here, and where is, yeah, P, yeah, I guess P has to be in there. But yeah, they're all pretty tight. Now, the last thing, the third aspect of biplots that is often useful is the relative location of sample points with respect to the variables. Data points falling near a label of a variable typically exhibit greater values for that than like what's average. This often helps in understanding why a certain observation may be an outlier or anomaly. For instance, the Wynne-Darling data set, those schist samples in the biplot that were in the upper left corner, these are richer in silicone oxygen 2 and aluminum 2 oxygen 3 than the average of the data. And so let's double check that. Let's look at the biplot and notice that these here are closest to aluminum and the aluminum 2, oxygen 3, silicone, oxygen 2. So these are closest to here, and I've got some purples over here. So this cloud of schist data points look like they'll have greater values of those two. And so let's confirm that. So here I'm just going to go through and calculate the average of the different compositions. And we're going to focus on silicone oxygen 2. Well, hey, that's much bigger. And Al2O3. Now, this is, you know, this is not as proportionally as big as this one, but remember the basalt is one data point or nearly one data point. So there's very little data here. This is, we can just view this as an outlier, and we can see that proportionally there's a lot more here. So, you know, that's a neat trick. So we got three things going on when we look at biplots that are super, super useful for us with our composition data. And so if they're on, if three or more components form a line, then we know that we have like a one-dimensional trend in our ternary plot. If two labels are very close to each other, then they're practically proportional, and these variables will be showing up on a line in the ternary plot. And if we see that if we see dots that are close to the actual arrow label, we know that they're going to be proportionately larger in that particular variable. And so this is a huge win for us to look at the biplot and be able to figure out what's going on. All right, well, that's all I've got for you. Life is short. Do math.